Welcome to The Explainer. Today we're going to jump right into one of the most important tools in all of machine learning, linear regression. Now I know it sounds a little intimidating, but I promise by the end of this, you'll see it's a really clever and powerful way to find patterns and make predictions from data.
So let's kick things off with a huge question, one that really drives a ton of AI. How can we take the information we have right now, today, and use it to make really smart guesses about what's going to happen tomorrow?
To get our hands dirty with this, let's use a super simple real-world example. We're going to see if we can predict a car's fuel efficiency, its miles per gallon, or MPG, using just one single piece of information, how much the car weighs. Okay, so here's a peek at the kind of data we're talking about. It's pretty straightforward. In one column, we've got the car's weight. That's our input. And in the other, we have its actual MPG, what it gets out on the road. The whole game here is to figure out the hidden relationship between these two numbers.
But here's where it gets interesting. When you just take all those data points and throw them onto a simple graph, bam, a pattern just jumps right out at you. These dots are not random at all. You can clearly see this downward trend. The heavier the car, the lower its fuel efficiency. And that relationship right there is the key to everything.
All right, so we see a pattern. But how do we actually turn that visual clue into a tool that can make a prediction? The answer is we need to find the one single straight line that cuts through that data in the best way possible. And there's a name for this technique. It's called linear regression. It's what's known as a supervised learning method, which is just a fancy way of saying it learns from examples where we already know the right answers. Its entire job is to find that perfect straight line that describes the connection between our input and our output. Okay, don't panic. I know this looks like something straight out of algebra class, but trust me, it's way simpler than it looks. All this equation is really saying is that our prediction is equal to some starting point plus the steepness of the line multiplied by whatever our input is. That's it. So how does a machine actually learn those perfect values? Well, it's pretty cool. It basically starts by taking a wild guess, and then it measures just how bad that guess was. And in the world of machine learning, that measurement of wrongness has a name. We call it the loss. Right, and this loss is exactly what it sounds like. Think of it like a penalty in a game. For every single car in our data, the model looks at the gap between its prediction and the real MPG. The loss is just a single number that sums up how wrong it is across the board. The entire goal of training is to fiddle with that line until the loss score is as close to zero as humanly or, well, machinely possible. And what's really cool is that there isn't just one way to calculate this penalty. A really common one is called mean squared error, or MSE. The key part is that it squares the error for each mistake. What that does is it massively punishes big mistakes. So if the model is way off on one prediction, it gets a huge penalty, which forces it to pay extra attention to those big screw-ups. All right, so the model knows its score. It knows how wrong it is. Now what? How does it actually get better? Well, the magic behind that is a process called gradient descent. This right here is the learning engine for a huge number of AI models. And gradient descent is really just the simple but incredibly powerful rinse and repeat cycle. First, it calculates the loss for its current line. Then it figures out, okay, which way should I nudge my line? A little steeper, a little flatter, to make that loss number go down. Then it makes that tiny adjustment. And then it just does it all over again, and again, thousands and thousands of times. You know, the best analogy for this, seriously, is picturing a ball rolling down a hill. Imagine the loss score is a huge valley. The model starts somewhere up on the side of that valley. Each one of those little adjustments is like the ball taking a small roll downhill, always looking for a lower spot. Eventually, it finds its way to the very bottom of the valley, where it can't roll down any further. That's the point of minimum loss. And you can actually see this learning happening. If you plot that loss score after every single step, you get what's called a loss curve. It almost always starts off really high, then drops like a rock as the model figures out the basics, and then it slowly flattens out as it makes tiny, precise adjustments. That flattening at the end, that's what we call convergence. Now here's the thing. We're not just passive observers here. We actually get to control some of the settings for this whole learning process. These are called hyperparameters, and they help us guide the model to learn better and faster. And probably the most important one you'll ever tweak is something called the learning rate. This is super simple. It just controls how big of a step that ball takes as it's rolling down the hill. And getting this setting right is absolutely critical.
So if your learning rate is too small, it's like the ball is taking these teeny tiny microscopic steps. It'll get to the bottom, for sure, but it's going to take forever. It's just a huge waste of time and computing power.
On the other hand, if your learning rate is way too big, the steps are huge. The model just leaps from one side of the valley to the other, completely overshooting the perfect spot every single time. It just bounces back and forth and can never actually find the solution.
But when you get it just right, that's the sweet spot. The model takes big, confident steps when it's way off, and then smaller, more careful steps as it gets closer. It finds the best answer quickly, smoothly, and efficiently.
So after all that, after the loss and gradient descent and learning rates, you might be wondering, why does drawing a simple straight line through some dots matter so much?
It matters because this process, this core loop of measuring your error and then taking a small step to fix it, this is the absolute bedrock of so much of modern AI. It's the same fundamental idea that powers those massive, incredibly complex neural networks you hear about that can write text or create images. It all comes back to this.
And that really leaves us with one final kind of mind-blowing thought. If a machine can learn something this useful just by trying, failing, and getting a little bit better each and every time, well, what else can it learn? Once you really get this one idea, you've opened the door to understanding the entire world of artificial intelligence.